This video is on section 8.3 notes, nonlinear systems of equations. So in this chapter so far, when we've talked about systems of equations in 2 variables or 3 variables, and what we're going to do in the next video, and we're going to talk about inequalities, most of that is something that you probably learned in high school, and it's probably familiar. You might have been exposed to this in high school, but quite possibly you weren't. So nonlinear systems are a system of equations, so 2 or more equations, that has at least one nonlinear equation, which means that one of the equations is like a parabola or an exponential function or an absolute value function or just something else. So nonlinear systems might have solution sets which contain more than one point, and that's because if you have a curved line, then a curved line could intersect a straight line at more than one point. So when we look at these, we don't know necessarily exactly how many solutions they're going to have. We're going to have to rely on our prior experience so that we know, oh, I'm solving a quadratic equation this time, I should get 2 solutions. Or I'm solving an absolute value equation, I need to make sure that I'm doing the positive version and the negative version. Or I'm solving a logarithmic equation, I need to check for extraneous solutions when I do my answers. So this section is going to be more difficult in that regard because we're going to have to think about what we've learned in the course so far and keep that in mind as we solve equations. I put pictures here for each problem. You will not have access to these pictures. Like, they're not just going to be, they don't just give you the system and then always give you a picture, but you're always welcome to graph them if you're able to kind of see what's going on. Obviously, you shouldn't be getting the answers that way because we're learning how to do these by hand, but if you want to see the graph so you can see what's happening, I'm totally fine with that. So typically, one more thing before we really get going in the examples is that typically our method of solving these is going to be substitution. Elimination doesn't work as well if you don't have equations that are set up exactly the same way with like terms. So substitution is pretty much the only method we're going to be using here. Okay, so for this problem, I can already see that this y is alone, x squared plus 1, and so I can take that and substitute what I know it equals in for y. So I have x squared plus 1 minus x equals 2, which means that the type of equation that I'm going to be solving is an x squared equation or a quadratic equation. And I know that when I solve those, I always want the equation to equal 0. And then my method of solving is either factoring or the quadratic formula. So I'm going to go ahead and subtract the 2 over. And I'm going to write this in the correct order. So I'm looking for 2 numbers that multiply to -1, that add to -1 if I'm factoring, and that's not possible, which means that this is a quadratic formula problem. So I've got x equals the opposite of b, so +1 plus or minus b squared minus 4 times a times c divided by 2 times a. So the discriminant is 5. Okay, so what I just found is I just found the x coordinates for both of these points. X coordinate over here, x coordinate over there. So I have 1 plus root 5 over 2 and 1 minus root 5 over 2. And I am not sure if my math lab is going to let you use decimals, but I'm guessing not. I'm guessing my math lab is going to make you write these answers in exact form, and so I'm going to go ahead and find those first, but then we're going to label the picture with the decimals. So to find the y coordinate, you can use either equation and make sure you use the easier one. So here we have y minus x equals 2, which we can think of as y equals x plus 2. And so if y equals x plus 2, I'm going to take this 1 plus root 5 over 2, and I'm going to add the whole number 2 to it. And the whole number 2 is just the fraction 4 over 2. So I'm adding 4 over 2 to this problem. So if I have a common denominator of 2, and I add the numerators together, I have 1 plus root 5 plus 4. So I have 5 plus root 5. For my second answer, I have 1 minus root 5 over 2 plus 2. The 2 I can think of as the fraction 4 over 2. So I have a common denominator of 2. And then I'm going to add my numerators together. 1 minus root 5 plus 4 would be 5 minus root 5. Okay, and then if we wanted to just put these in their decimal form, actually let me type this in as a fraction, 1 plus root 5 over 2. Then to get my y coordinate, I would just do this x value plus 2. So that's this one right here. So this is the point 1.618, 3.618, and then we have negative 0.618, 1.382. So if my math lab happens to take those as decimals, then those would be your decimal answers. If my math lab forces you to have exact answers, that was how we found the exact answers. Okay, let's try the next problem. So this one has two nonlinear equations. You have a parabola and you have an absolute value graph. And I really had to zoom in and make this scale kind of wonky so you could see all the solutions. But there's actually 4. There's 2 here and then 2 over there. So we're about to find a lot of answers. So here we know that y equals the absolute value of 3x. We also know that y equals x squared plus 2. So since we know that y equals both of these things, then we know that both of these things are equal to each other. Y equals y, and so absolute value of 3x equals x squared plus 2. So absolute value of 3x equals x squared plus 2. And then we just have to remember back to when we learned about absolute value equations, that whatever's in the absolute value, it could spit out the positive version of the equation, but it could also spit out the negative version of the equation. And so we have to write both of those down and solve both of them. So 3x can equal the positive version, and 3x can equal the negative version. So this is a quadratic equation, and so is this. We're going to get 2 answers for this one and 2 answers for this one. So this quadratic equation, of course, we want to make it equal 0 so we can solve it. So we have x squared minus 3x plus 2. And thank goodness there are 2 numbers that multiply to positive 2 and add to negative 3. Those 2 numbers are negative 2 and negative 1. So this problem, we didn't have to use the quadratic formula. It factored nicely. X minus 2, x minus 1. So x is 2, x is 1. Okay? And then over here, we have 3x is negative x squared minus 2. I'm just distributing that negative. Again, we have a quadratic equation, and I want to make this equal 0 so I can try to factor it. So I'm going to take the x squared and move it to the left side. I'm going to take the 2 and move it to the left side. So I have x squared, positive 3x, positive 2, all on the left side, equals 0. I'm going to try to factor that. So I'm looking for two numbers that multiply to 2 but add to 3. And again, thank goodness, it works. 2 and 1 multiply to 2 and add to 3. So I have x plus 2 and x plus 1. I don't know why I wrote it like that. Okay, so my two solutions are -2 and -1. So now we just have to take this and write our coordinates. And to find the y coordinate, you can use whichever equation is easiest to plug these values into and get your solutions. So over here, the first x coordinate we have is 2. Absolute value of 3 times 2 is the absolute value of 6. The positive version of 6 is still just 6. Next we have 1. 3 times 1 is 3. The positive version of 3 is still just 3. Over here we have -2. 3 times -2 is -6. The positive version of -6 is positive 6. Then we have -1. 3 times -1 is -3. The positive version of -3 is positive 3. So if we were to label these points with their solutions, we have 1, 3, 2, 6, -1, 3, -2, 6. Okay. All right, so this next example has two non-functions. These are not functions, so they don't pass the vertical line test. One is one that we recognize, x squared plus y squared is 25. That's that circle. The other is called an ellipse, which is the mathematical term for an oval. So it's just a circle that's been squished a little bit. And the program I use to create these graphs, and a lot of programs, have a hard time with parts of a curve that get really vertical because they're not functions. And so if you fill this in right here, the ellipse should have these parts connected. It just had a hard time. So they really are there. If you graph this on Desmos, you'd be able to see, like, yeah, they connect. Okay, so we're going to work with this one next. Before I go much further, I know a lot of students are uncomfortable with the denominator here, and so we can get rid of that denominator just by thinking about, well, if we multiply by 18, we could get rid of the 18th. If we multiply by 32, we could get rid of the 32nd. So I'm just going to see what those kind of have in common. 18 and 32, 576. Feels like that's a little large, but I'm going to go ahead and do it because I don't feel like thinking about this too hard. So I'm going to multiply this entire equation by 576, and I'm just doing that to get rid of the fractions because I don't want to deal with fractions. So for the first part, 576 divided by 18 is 32, so that would give me 32x squared. 576 divided by 32 is going to be 18. And then the 576 times the 1, obviously, is just 576. So at this point, my numbers are kind of large, but at least I don't have fractions. Okay, and I'm going to go ahead and do this problem as substitution. And so I'm going to isolate, I'm going to isolate y squared because I like when the problem is in terms of x's. So y squared, I'm going to subtract the x to the right side. Y squared is -x plus 25. And then since I know what y squared is, I'm going to take all of this and I'm going to substitute it in for y squared. So I have 32x squared minus 18x squared plus 25 times 18, 450. And 32 minus 18 is 14, so I have 14x squared and I'm going to get the x squared alone on the left side. So we'll get the x squared completely isolated. So x squared is 9, and so that means x is plus or minus 3. You have to be really careful here. It's very common for a student to be like, oh, the square root of 9 is 3. We have 2. We have positive 3 and negative 3. So if you look at this, you can see, you know, here's your positive 3, here's your negative 3, positive 3, negative 3. All right, and then I'm going to have to go back and plug this in to figure out what the y value is. You can use the second equation if you want. I'm going to go ahead and use the first. So y squared is the negative version of x squared. X squared is just 9, so it doesn't matter if you use positive 3 or if you use negative 3, you're going to get 9 no matter what. So it's negative 9 plus 25. So y squared equals 16, and that means y is plus or minus 4. And so we have to do all the combinations of this. We have to say positive 3 goes with positive 4 and negative 4, and we have to do negative 3 goes with positive 4 and negative 4. And it feels obvious because we can see the picture and we can see there's 4 points. But if you didn't have the picture, you'd still have to think through how this equation was working, okay? So if you were doing this without the picture, you would say, well, when I plug in positive 3, I get negative 9 plus 25 is 16. I get plus or minus 4. So when I plug in positive 3, I get plus or minus 4. That's 2 answers. And then when I plug in negative 3, the same thing happens. I get 2 answers. And so that's how you know without the picture that you should have had 4 answers total. So we have positive 3, 4, 3, negative 4, negative 3, negative 4, negative 3, 4. All right, and here is the last example. It says solve the system, and we have 2 logarithmic equations. So one of them, the first one, looks like this, and then the other one that has been shifted to the right and is upside down or reflected over the x-axis looks like this. So they only cross in one place. And right now they're both written where the y is isolated. And so since we know that the y's equal each other because they're the same variable, then we can say that these 2 must equal each other as well. So I'm going to say log base 2 of x plus 2 equals 1 minus log base 2 of x minus 2. And I don't know how to work with a log and a number. I don't know how to combine those. I don't know how, like, if there's some special trick for them, but I do know how to work with a log and another log. And so what I'm going to do is I'm going to take this log expression and I'm going to add it to the left side of the equation, because those 2 logs I can put together. They both have a base of 2, and I can use my properties of logs or my rules of logs to condense them or to rewrite them as a single logarithm. So that's what I'm going to do. I'm going to take this and move it to the left side. So I have log base 2 of x plus 2, and I'm adding log base 2 of x minus 2. And whenever you add logs together, it really means you're multiplying whatever's inside of the logarithm. So I have log base 2 of x plus 2 multiplied by x minus 2. And so I can FOIL those out. X times x is x squared. X times negative 2 is negative 2x. 2 times positive x is positive 2x. So we had negative 2x and positive 2x, and those are going to cancel. But I'll go ahead and show my work. So negative 2x and positive 2x cancel. And then positive 2 times negative 2 is negative 4. Okay, so I have log base 2 of x squared minus 4 equals 1. At this point, I'm going to go ahead and get rid of the logarithm, and I'm going to do that not by just canceling the log. I only have 1, so I have to undo the logarithm by using an inverse operation. So to undo the log, I have to do a base of 2 and a base of 2 on this other side. So base of 2 and log base 2 cancel each other out. I end up with x squared minus 4 equals 2 to the first power, which is 2. And typically I would say a quadratic equation, like what we have, should be solved by factoring or using the quadratic formula. But there were actual other methods that we learned in, I believe, the first chapter that we could use, and one was by taking square roots and the other was by completing the square. And we just don't often use those. We typically factor or use the quadratic formula because those are the most common methods. But I'm going to go ahead and use the method of taking square roots to solve this, which means I'm just going to undo each step. So I'm going to move the 4 over. X squared equals 6, and I'm just going to square root each side. I guess we did that on the last problem too. I just didn't think of it as a quadratic problem. And I'm just going to make sure that when I do this, I get the positive version and the negative version. So positive square root 6, negative square root 6. But then if I look back at the original problems, positive square root 6 plus 2, clearly a positive value. Positive square root 6 minus 2 should also be positive, but negative square root 6 is a problem. You can't plug in negative square root 6, especially here, negative square root 6 minus 2. So the reason we don't have 2 points of intersection is because this one right here is an extraneous solution. So positive square root 6 is going to be the x coordinate. And then to find the y coordinate, we just have to take that x coordinate and plug it back in. And so I'm going to use the first equation just because it has less stuff. So y equals log base 2 of root 6 plus 2. And there's nothing special I can do there, so that's just the y coordinate, and it's just kind of a weird number. But I can go ahead and find the decimals for those if I want to see exactly what they are. So we have 2.449. And then we have math up, log base 2 of square root 6 plus 2, 2.154. And there we go.